Hi everyone. Today I will talk to you about maximal reconvergence. Let's jump straight into it. Maximal reconvergence gives a well-defined answer to the following question. Which invocations in my subgroup are active for the purposes of non-uniform subgroup operations? And immediately you will ask me, okay, what does that mean? Okay, some caveats. This is a very technical subject, and I have 25 minutes, and the next speaker has made it clear to me that they want to have their talk too. I can't say everything I have to say about this, so yeah. The spec has very precise language because it has to. Instead, I will resort to oversimplification and lies. I'll try and signpost where the lies are. And I will mostly stay on the background side of things. I will not give you the precise spec language, because you can go ahead and read the spec, and it's much better than me at explaining the finer details. And hopefully this is more educational than me just babbling on from 25 minutes. Okay, right, we have to talk about what an invocation is. Spurdy has this complicated paragraph that you have probably already read. In simple terms, an invocation is, for example, the vertices of a vertex shader. You have 8 vertices here. They're gonna each run a vertex shader. So each instance of that vertex shader is what you call an invocation. In the case of rasterization, when you have a pixel that is, gets rasterized, you are going to execute a fragment shader. Again, each instance of that is an invocation. And when you're doing compute shader, it's very simple. You're dispatching a grid of invocations, and the grid is regular and it's nice and simple. There's also rays in ray tracing pipelines, so these also translate to one invocation. So generally, an invocation is what you would have as the smallest unit of execution on the GPU. When you write a shader, your local variables, your ifs, your whatever, that is all happening at the invocation scope. You also call it a thread or lane, and I might switch wording in this talk. Sorry, invocation is the proper Vulkan word, but I tend to call them threads. Okay, what is a subgroup? Well, your GPU is an extremely parallel computer, and what that means is you don't have one invocation in flight, you have 10,000, 100,000. You have many, many, many invocations, and that's why your GPU is fast, because it does many things in parallel. Your invocations, they get grouped together into subgroups. You will find subgroups referred to as wave or wavefronts. Again, everyone has their own terminology. Welcome to GPUs. And invocations within a subgroup get a local ID. So for those who are familiar with what a workgroup is, here the identifier of an invocation within a subgroup is only one-dimensional. This looks something like that. In red, you have the invocations represented as circles, and then you have their ID written down, and then the whole thing, that's your subgroup. So here's a small example of what that actually translates to. When you have 2 triangles, they get rasterized, you get a bunch of invocations. The invocations get packed together into subgroups. And note that the pink triangle actually isn't just in the first invocation, but also in the second one. And the second one even has blank space. And there's more rules as to how exactly that packing works, but that's not in the scope here. The point is, a fragment, a given triangle does not necessarily cleanly map to a clean number of subgroups. Invocations within a subgroup have the opportunity to efficiently synchronize and exchange data. This is what this talk is going to be about. But first, let's do a bit of a tangent about more scopes. So we've seen especially in the compute stage. Here you have an invocation, which we already described, the subgroup, which we also already described, and then there's that work group I talked about. A work group is basically a 3D grid of invocations, and that size is programmer defined, unlike subgroups, which are harder defined, and I forgot to say that. Work groups have access to shared memory, so again, that's some fast memory that is more local to the GPU, but it's not as local as subgroup memory. And then a work group is, of course, made out of subgroups. And then finally, you have the top level, which is cross-work group. So when you do a compute shader dispatch, you set the size in terms of a number of work groups in each dimension, and that's your cross-work group scope. So you can see that each scope is nested in the last one. Okay, so we're gonna have a small demonstration of what execution from a subgroup perspective looks like. Here we have a small program that doesn't do much of interest, do something very interesting. It just adds together 2 numbers that are consecutive in a buffer and then writes them to a destination buffer. And it's using the subgroup, so the local in the subgroup invocation ID to access, to determine the identifier. We're going to run 4 invocations of the shader, and we're going to pack them together in one subgroup. We're going to step through the code and see what happens at each step. So in green here, there's green overlay. That's your instruction pointer, so to say. So this is where execution is currently at. Here you have the values of the global variables, which are just 2 arrays of size 4. And then here in the bottom, you have the values of the local variables. And you'll note that these are angle brackets, not square brackets. And what I'm trying to say here is that for each of the local variables, you get the value for each invocation in a list. So you have invocation 0 that corresponds to the first element, 1 to the second one, and so on. So let's get going. So the first instruction just fetches the subgroup local subgroup invocation ID and puts it in the ID variable. So you can see we get 0, 1, 2, and 3. Second instruction just adds 1 to it and then takes the result of modulo 4. So you get 1, 2, 3, 0 this time. And then we are going to access the buffer. So for invocation 0, you're going to take the value at 40 and the value at 2, add them together, you get 42, 69, 42, and then 15. And finally, you store that to your destination buffer, and that you can later read that back on the CPU or whatever. And this is what execution from a subgroup perspective looks like. So what are subgroups really? Well, if you're familiar with vector programming, subgroups are basically SIMD, and that's where the lives come in. It's not really SIMD, but it can be. It depends on your hardware. It's I would call it a good approximation, but don't take this further than you need to take it. And the SIMD thing lets me describe group operations. Invocations have the opportunity to use group operations to exchange data efficiently within the subgroup. So here you can see some weird abstract processor. It's executing a whole subgroup at once. And in here you have the vector registers, which means you can efficiently exchange data between invocations that are running on the same SIMD unit without going to local global memory. It's very cheap to exchange memory like this. So let's do a quick overview of the subgroup operations, group operations Vulkan has. First, you have elections, which are going to, if you do a subgroup elect, you're going to get false for every thread except one, so-called the first one, which is going to be the one with the lowest invocation ID. You can also do a ballot, or also known as a vote. What you do is you have a Boolean condition that every thread computes, and then you take the result for that condition for every thread and you pack that in a big bit mask, and then everyone can see the answers of everyone else. And you can do things such as count the number of active bits to know how many invocations satisfy a given condition. Then you have shuffles where you're directly exchanging data with other invocations. So here you can use it to reorder a string, for example. You can do also shuffles up and down. You can exchange data with your neighboring threads directly. And then finally, there's arithmetic operations, which, for example, let you do reduction. So you can do subgroup max, and that's going to give you the maximum value of a given variable for all the invocations in a subgroup. You can also do a subgroup add, which will add all these values and give you the result. There's also inclusive and exclusive adds, which I will mention again later, but they're really useful, trust me. Okay, so I've modified my example a bit here. Now there's a subgroup max after the first ID line. Let's look at what it does. Well, we have 0, 1, 2, 3, and now we have 3 everywhere because we asked for the biggest value of ID in the subgroup. That's 3, and that's what everyone gets. If we proceed, the NID variable gets also the same value for every invocation because all of its inputs are the same. And then the sum, again, is the same, and you store it, it's all the same. Brilliant. So that's the group operation in non-uniform group operation at the start. What about the uniform bit? What is that? What do we mean by that? Okay, there's really 2 sides to this. The first one is you can describe uniformity when talking about a variable. And here, oh boy, these slides are not too clear. So the red variables, if you can read that, these are the ones that are non-uniform. Their value is different for every thread. And the blue ones, they are the ones that are subgroup uniform. Their values are the same for every thread. And technically, you could just only store 1 copy of these per subgroup if you wanted. So when you have variables that have the same value for every invocation in a subgroup, you call that subgroup uniform. And then there's control flow uniformity. So I've modified the program again. And this time we end up with negative values in our sum, and we have a condition on whether our sum is negative. And then something weird here needs to happen because we are executing the entire subgroup as one, but obviously we can't do that here. So something weird indeed does happen. It's called divergence. We are only going to run this code for the threads that satisfy the earlier condition. So we can, here I've described the active invocations. The first one is disabled, the second one is enabled, disabled, enabled. And there, what we've done is we've created a subset of our work group. This is known as non-uniform control flow. Not every invocation in the subgroup is executing this. Then, at some point, we can continue executing, we can return to uniform control flow because every invocation is supposed to run this. This is the reconvergence part of maximal reconvergence. So let's go over this again quickly. You can say that a variable is S uniform for a given scope S if all the active invocation store the same value. For example, if we have the following variable X with 0 in every invocation, that is subgroup uniform given a subgroup size of 4. Then the spec has this word called tangle, which it sounds scary, but it's basically a set of invocations that are executing together as one. So your execution of your shader always starts with subgroup uniform control flow. All of the invocations in the subgroup are in the initial tangle. And then control flow, you can say it's uniform if there's only one tangle, if there's only one set of threads trying to execute something for a given scope. And also earlier I showed you the nested scopes that you have, for example, subgroups that live inside workgroups. That does mean if you have something that is workgroup uniform, it is also subgroup uniform. And if you have a constant, it's uniform for everyone because it's a constant. And a nice caveat for some of those who caught it earlier, if you're doing two subsequent draws, even if something is uniform for that draw, that doesn't mean in the shaders it's going to be subgroup uniform because you can actually merge different draws together. And that's a caveat, that's an advanced caveat, but I figured I should point it out. Okay, so now let's talk about the non-uniform side of group operations. They're called non-uniform group operations because what happens is defined even if you're not in uniform control flow. So if you're doing an election and the first thread in the invocation is inactive, well, it can't be elected, so instead the second one gets elected. So in general, only the active the inactive invocation, sorry, they're going to return false when you're voting. They're skipped when you're doing reductions. And if you try and shuffle from an inactive lane, you get an undefined value. So here, this subgroup add here, it's not actually adding these interrogation marks. It just ignores them and sums the other numbers. So let's look again at divergence and reconvergence. So as we said, you start out with uniform control flow. Every thread is active. Every invocation is active. You can see them here. They're all red. Divergence is what's going to happen when you execute this non-uniform branch here. You have different destinations for different invocations, so you split the tangle into two. And then after that, you reconverge, of course. So you split it into two. And after that, once you're done with the branch and everyone is supposed to execute the same code again, you reconverge. And the thing is, where exactly reconvergence happens under any circumstances is typically left either nothing is said about it, or it's explicitly undefined, or it's underdefined. So maximal reconvergence in Vulkan, before that, it was underdefined. It was defined in certain cases, but not all of them. And for an instance of what I mean by it's underdefined, well, this is the behavior I've been showing you, but what if you executed it like this, where you keep on executing the rest of the shader with two different sides, like with two different tangles? I mean, you could technically do that. The shader will still run correctly as long as it's not using subgroup information. No. Well, what maximal reconvergence says is actually, no, this is what you're supposed to get, and this is the only valid thing you can get. All right, so the maximal reconvergence rules, what are them? Basically, they're defined on top of structured control flow, which you are very familiar with if you've written C or GLSL or basically anything. These are your if switch, your for while, you return, your breaks, and your continues. These are the structured programming keywords everyone is familiar with. Generally, the idea is you diverge when you will enter one level of such nesting. So if you enter an if, that's divergence because you have two sides you can enter, so you're partitioning your tangle. And then you're going to reconverge once you go outside of that block because Now you have things you can merge together. And whenever possible, we try and the spec make sure that this tangle, this set of threads that are executing together, it's as big as possible to maximize efficiency. And that's why it's called Maximal Reconvergence. Or at least I think so. Someone can correct me if I'm making that up. So we already seen how ifs work. You basically partition the set according to the condition. This is the same as before. Here you will note that we do have a non-uniform subgroup operation on the right side. So it is very important that only these threads participate in it. Otherwise, we will get the wrong answer. And you can also nest ifs. And this is one of the things Maximal Reconvergence defines properly that wasn't defined before. If you nest ifs, it still works the same way as if they were not nested. So here you partition the tangle into two. On the left side, you get one thread active. On the right side, you get three. And then you partition it again. And then only this middle side is going to do something relevant with the subgroup. And then you reconverge progressively. So first you reconverge the inner if, and then you reconverge the outer one. And I don't know why there's one missing step of animation. Okay, let's keep going. While and for loops are basically the same thing. Here I've drawn the code a bit funny because I'm actually drawing the control flow graph with my arrows and my little boxes. So you have the start of your shader, which is uniform control flow. Then you have the loop header, which is where you make the decision whether you want to stay in the loop or not. Then you have the loop body. And then at the end, you have the end of your shader. So you enter with all your threads active as before. And immediately in the loop header, you make the decision, you know what? Thread number 3, it doesn't want to be in the loop. It doesn't want to have fun. It's just going to wait for everyone at the end. And so you proceed into the loop body with your 3 remaining threads. And you return to the loop header where, you know what, thread 1 is also done with this stuff. It is also going to wait. Then you go back inside the loop body with your 2 remaining threads. They do their stuff. You exit back to the loop header. And then at the end, everyone reconverges and you execute the end only once. And again, Maximal Reconvergence provides a guarantee that this specific behavior happens, nothing else. So let's look at a couple of examples. Let's say we want to efficiently append data to a buffer. On the left, we have the simple shader that just computes some data somehow. And then it does an atomic add on the size of the destination buffer with a 1. And what that does is that it's going to increment that size and it's going to return the old value. So where the old value was, there's nothing. We can write our data there. And that's how you can atomically write to a buffer with, making sure there's no gaps or anything. This is straightforward. The only problem is, of course, every invocation is going to do one atomic add. So that's a lot of atomic adds. That's a lot of they're gonna fight over it. I forgot the proper word. And yeah, contention. Thank you. Someone in the audience saved me. So there's a lot of contention. On the right side, we do a lot more work. First, we count how many invocations are trying to write to the buffer. Then we do this exclusive add. So an exclusive add is every invocation is going to get the sum of all the invocations whose ID is lower than them. So for thread 0, you get 0 because there's nothing underneath. For thread 1, you get the value for thread 0. For thread 2, you get the value for thread 0 plus thread 1, and so on and so forth. So that if you do an exclusive add with 1, that means all the active invocations will basically enumerate themselves. One will get 0, one will get 1, and so on and so forth, up to count -1. Then we elect one thread, so only one thread will do this. And what it does is it does an atomic add of the size of the count of how many threads we need. And what that means is you basically get a range of entries into the buffer that don't have any data. And then we do a subgroup broadcast first to make sure that every invocation can see that value. Because right now we just computed it. It's only available to the whatever thread was elected. We want to make sure it's broadcast for everyone else. And then we can just every thread can add the base and the index and write the data in parallel, and you only had to do one atomic add instead of however many invocations are in your subgroup. So we've possibly improved performance a bunch. The second example is actually a pattern. It's called a scalarization loop. The idea with this shader is we're doing some descriptor indexing, but we don't have the non-uniform descriptor indexing feature enabled because maybe it's not supported or something. So we have an array of textures, and we have a texture identifier that every invocation is going to get. And that texture identifier is non-uniform. Here I've drawn what texture each thread is trying to select. With the scalarization loop, we're going to solve the problem that in Vulkan you're not allowed, if you don't have the appropriate feature, you're not allowed to do this sample directly. You have to sample from the same texture unless the feature is supported. So what we do is we have a loop, and we're going to pick one invocation, and we're going to ask it, okay, tell everyone else which ID you would like to sample from. And then everyone else is going to compare their value of their preferred ID to sample from. And if it's the same, then they're going to actually do the sample together, but only those threads. That's what the if is doing. And then they're going to break out of the loop. So let's say in the first iteration, the thread in charge says, well, I want to sample Bliss. And so all the threads that want to sample Bliss do that. And then they break out of the loop. And then you have to pick another one. So maybe you pick the window wallpaper. And well, all the threads that wanted to sample the window wallpaper do. And again, and then at the end, what you will have done is you will have iterated over the unique values for that non-uniform variable. You will have run as many iterations as you have different values in that variable. And that means that in each one of these iterations, you get the chance to do something uniform with the subset of the threads for which this variable has a uniform value. And that is very powerful, and that is very useful, and that's actually how non-uniform descriptor indexing is implemented on some hardware. So that's a really cool pattern. Okay, so why does any of this matter, really? Well, in theory, you have the issue that you have these non-uniform group operations, and you said, well, they have a precise behavior if you have divergent control flow. But if you don't define what divergent control flow exactly does, especially what reconvergence does, well, these non-uniform group operations don't do anything. They're still underdefined. So that's the theoretical issue. What about in practice? Well, in practice, if you write a simple example and you don't enable maximal reconvergence, it probably will work even without the feature. The tricky part is if you write some more complicated code, maybe you wrap whatever you were doing into an outer loop, well, suddenly the compiler breaks your stuff. And that means that writing code at scale that does subgroup stuff and relies on specific divergence behavior, that is just not doable without maximal reconvergence. If you use some operations wrong if they expect uniform data and you feed them non-uniform data, you can get undefined behavior or crashes. So this is not really just a performance concern, it's a correctness concern. Maybe you care about this, maybe you don't. Okay. So this is really the killer feature you've never heard about. In the words of Tom Olson last year, subgroups now work the way you thought they did. And yeah, I know it was already used. I'm sorry, I didn't know that. And what that really means is that the behavior of your code follows its structure, and that allows you to write your collaborative algorithms in a natural way. And it guarantees that the compiler optimizations will not get in the way. There's CTS that actually checks against that. And I think this belongs on the shortlist of why Vulkan is awesome, alongside buffer device address and descriptor indexing, my two other preferred features. Right, so who has this? Who else has this? Well, OpenGL doesn't even have non-uniform group operations. Nope. OpenGL, well, you're at the mercy of the compiler. It's underdefined what reconvergence is, so it's whatever the compiler wants to do that day. DirectX is the same, Metal is the same. CUDA is different, works on a different model. You have a bit mask that represents which invocations you're trying to communicate with. It's fine. I don't really like it, but that's just my opinion. It's different, is what I'm saying. It doesn't compare directly. So that means that Vulkan is the only API with this feature today. Hooray! So now I have to suggest some reading to you, and I Googled it and desperately trying to find some cool references, and turns out there's not that much. Alan Baker has written a blog post about maximal reconvergence for the release of the extension last year. That's pretty good. You should check that out. I also will tell you, well, now if I manage to pique your interest, just go look at the specification, the Spurvey one specifically. It's not as bad as I make it out to be. It's actually fairly readable and it's small. And then there's a post from Faith. Hi, Faith. We actually did implement maximal reconvergence on NVK, which, if I understand correctly, and she's looking at me, it's sort of basically implementing it on top of the CUDA model with masks. Yes, it is cool, and that's pretty enlightful. So I suggest you read that if you're fascinated by this topic, like I am. And I am now able to take questions perfectly on time.
Question back here. Not so much a question, but more of a comment. And I'm afraid I have to burst your bubble a little bit. But Microsoft have publicly said on a number of occasions that HLSL does work like that.
Yes, but
They don't have a spec for it.
their compiler
And their
is using a
testing is-
representation that cannot account for it yet. So unless they switch, until they switch to SPUR-V, I'm going to keep that in the slides.
They do run on top of, like, they have a Vulkan implementation on top of DX, which they run through it, and that is how they validate it right now. So they are validating it, and it's there.
I'll see.
So in my case, let's say I had like 4 compute shaders. So I want to do compute work and I wanted to change color formats, video scale, and all that stuff. Would you recommend this approach for combining that into one using this? So I'm not passing through multiple compute shaders.
I'm not sure what you're asking exactly.
So for example, like let's say you wanted to work with 4 pixels at a time. And in this case, you're going to color convert them, scale them,
Does the value of the computation depends on the neighboring pixels?
It might in some cases.
Then it might be a use case for subgroup operations.
Thank you.
I'm going to be a very horrible person
Go ahead.
and ask you, what's the interaction between this and helper invocations? Because helper invocations, you're not supposed to observe any side effects from.
I reserve the right to silence.
Okay. Can I pack in another one? Right, sorry.
Firstly, helper invocations suck. But they actually do work with subgroup operations. There was a lot of confusion about this, but with Maximal Reconvergence, we actually changed it so that to say specifically helper invocations participate in subgroup operations.
Okay, so you can actually see the side effects.
Yeah, well, they're not side effects. So like they still wouldn't write to memory, but they can talk to each other because the whole point of a helper is to basically do derivative operations, which are a sort of light version of subgroup operations. So that's why it's carried through.
I was trying to be nice and not bring that up. That's the scary part. You don't want to talk about the scary part.
I have a question here.
Does branchless programming avoids these issues?
I mean, yes, the name branchless means you're trying to avoid divergence in the first place. What often I've seen in these patterns is you're trading control flow divergence for basically implementing linearization yourself, which is when you're running both sides of a branch and you're picking the result. So at the end of the day, if you're doing different meaningful works on different invocations, you are going to see divergence one way or the other.
Okay. And so is it optimized to do so, or will it take longer time to just do branchless because it's more?
Well, it's gonna depend on the use case. Maybe you have like a clever bit trick you can do that actually avoids a branch because you're adding some integer to something instead of executing a conditional. That might help. It's just in general, that there is some unavoidable divergence.
Super fast. So for the platforms that don't get their drivers updated, etc., if I want to have maximal reconvergence and the extension is not going to ship, is it possible for me to fix all that by just peppering subgroup execution barriers everywhere?
I don't think it is. My personal opinion on this is that this really needs to be fixed. At the IHV inside the actual driver, you need the shader compiler to understand it. Otherwise, you're forever, chasing a goose around, and you will always be one step. I mean, you can look at the heroics. I've seen some HLSL blog posts where they try and like fight the compiler with hidden like fake branches and stuff. Like it's just impractical. You really want to be doing this quote unquote correctly, and I don't think it's hard to do correctly. It's just if you're on a abandoned driver island, good luck to you. Best of luck.
Thanks to our speaker.